Hi, this is a quick video on how to do some of the homework questions in StatCrunch for week 14, or if it's not week 14 in your semester, it's the homework from chapter 7 and chapter 8 on differences in means and proportions. Alright, so let's start off with what's currently homework question number 4, but it's 7.2, number 15. The T at the end indicates that the question expects you to answer this with technology, so let's do that. Here's the data table. We have two different groups. The sample size is 20 for each. The sample means are given here, and the standard deviations here. Your numbers, of course, will be different. It says, the researchers theorized that children who receive an AV presentation will have the same mean recall of the ad information as those who just received the visual aspect of it. Alright, so what's the hypothesis? Well, if we want to test to see if the means are the same, the alternative would be that the means are just different, because they don't give us that one's higher than the other. They just say that the null hypothesis is that they're the same, so by default the alternative would be that they're different. So that's our answer for part A. Okay, it wants us to find the test statistic. So let's go to StatCrunch, and you can access this with the question help. Alright, then just go to, when you're in StatCrunch, almost always you're either going to use the Stat menu or the Graph menu. Since we want to do statistics, we're going to go to Stat. We're dealing with T-stats, and we have two samples we're trying to compare. And we don't have the raw data set, we just have the summary information. So for the first group, let's pull up the data table again. For the first group, the sample mean was 3.71, the standard deviation is 1.97, and the sample size is 20. For the second group, the sample mean is 3.31, the standard deviation was 2.12, sample size is 20. It doesn't specify whether or not it's reasonable to pull the variances or not, but for the homework, they assume that the software you're using is going to pull the variances, so just select pull variances. And this is our null and alternative hypothesis that we figured out in the first part. If we were asked to do a confidence interval, we'd select that option instead, then click compute. And so these are our results. Our test statistic is 0.618, etc. Okay, let's go back to the question. We went around to 3 decimal places, so 0.618. It wants us to establish the rejection region. Because we are dealing with a two-tailed test, because our alternative hypothesis is a not equal to, we know the answer is going to either be this, what for me is option C or option D, but we don't know which one. So as far as the, we're going to need to use the t-table. There's actually two ways to do this. One way is with technology, the other way is with the t-table. There is going to be an option when using, there's going to be an issue when using the t-table, which I'll show you in a moment. Alright, so here's our table from the final exam formula sheet. Our degrees of freedom is actually 38. It's the first sample size plus the second sample size minus 2. And if you weren't quite sure of that, if you go to our output here, it says the degrees of freedom is 38. So that's what we want to look up on the table. However, you can see here that we have one with the degrees of freedom of 30 and the next one's 40. So 40 is the closest. This will give us close to the correct answer, but not exactly the right answer, but it's okay because it's multiple choice. And they asked us to test this, I believe, at an alpha value of 10%. Let me just go back and check real quick. Yeah, it says to test this at alpha equal 0.10. So since it's a two-tailed test and our alpha value is 10%, that means 5% is in each tail. So we have to divide it by 2 because it's a two-tailed test. So we're looking for the column with a subscript of 0.05, which is the second column, so T subscript 0.05, and we want the row that has degrees of freedom as close to 38 as we can get. And we get our test statistic is 1.684, and that's the positive side. The negative side would be negative 1.684. And I'm sorry, I don't mean test statistic, I mean our critical value. All right, so the closest option would be C. Okay, if you wanted to use technology to do part C, again, going back to StatCrunch here, we just need to find the t-value where we have 38 degrees of freedom, and the area to the right is 5%. So I'm just going to go to Stat Calculators. I want to calculate a t-value, and I want 38 for my degrees of freedom, and I want the area to the right, so I'll do greater than sign, to be 0.05, and I want to find what this number is here. So I click compute, and it tells me it's 1.686 approximately, which is what the answer is here. All right, so either way, tables or technology can get you this answer. So we want to make the appropriate inference. So our test statistic was 0.618. Our critical value was 1.686. So roughly looking at this graph here, the idea is that our test statistic is about here at like 0.6. And our critical value, our rejection region, starts over here. And mind you, there's also one on the other side, but that really doesn't matter since we're looking at a positive test statistic. Anyway, clearly our test statistic does not fall in the rejection region, so we're going to fail to reject HO, which means there's insufficient evidence that there's a difference between the two groups. So I'll select the insufficient evidence option. All right, they tell us here that the p-value is 0.54, so that means if we compared that to alpha using the alpha p-value approach, alpha is less than the p-value, or you can look at it as the p-value is greater than the alpha value. Either which way you look at it, this means, so since the p-value exceeds the alpha value, there's insufficient evidence to reject HO. Okay, last part here, what conditions are required for the inference to be valid? So we need the population variances need to be the same. We need both populations being sampled from our normal. We need that because of the small sample size. And because we're not doing a paired type test, we need each sample to be independent. Okay, let's move on to the next question. The next one I plan to do is number 5. And again, I might change this from semester to semester, but for the current semester, it's number 5, which is question 7.2, number 23. And again, you see that it's asking you to use technology. So botanists place seed baits at 5 sites, all right. The data is in the table below. Is there evidence to conclude that there is a different, to conclude that a difference exists between the average number of ant species found in each of the 2 regions? So similar to the previous one, we're just trying to see if mu1 is equal to mu2 or if they're different. This is equivalent to saying that if we took the difference between them, the difference would be 0. The alternative would be that the difference is not 0. Okay, we're going to do this one very similar to how we did the previous one. Just go to Stat, T-Stats, sorry, 1 second. Looking at the table here, we actually have a data table. So instead of copying all this information over, which would be maybe a pain, we don't have the summary statistics this time, we have the raw data. We can actually just open this in StatCrunch, and that'll make this a little bit faster. All right, so sorry, going back, we go to Stat, T-Stats, we have 2 sample. This time we have the raw data, so we're going to use that. Looking at how the data is organized, let's just move this aside for a moment. It's not The column labels aren't as descriptive as I would like. We see here that it's not arranged in just 3 neat columns. It's divided into 6 columns. Not the best layout, but that's all right. The site numbers are just like, they're just numbering the sites 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's not what we're trying to analyze. We're trying to compare the number of ants in the first region to the number of ants in the second region. So fortunately, the way StatCrunch works, even though the columns are all labeled the same, the first one is associated, the first number of ant species is associated with region A, and the second one is associated with region B. Again, there's nothing in the directions to indicate you're supposed to do this, but just select the pool variances option. This will give you the correct answer according to the homework. And this is exactly what we want to test for an hypothesis. Click compute, and this is all the information we should need. All right, so let's go back to the question. Okay, so our test statistic, it wants us to round to 2 decimal places, is 0.22. The p-value is 0.83. 0, it says to round to 3 decimal places. So since the p-value is quite large, bigger than any alpha value that we'd pick, we would definitely say fail to reject HO. They tell us that our alpha value is 5%, so our p-value is bigger than this alpha value for sure. So we do not reject HO, and there's insufficient evidence to say there's a difference between the number of ants in each group, the mean number of ants in each group. All right, let's look at the next question, number 8. Okay, this one deals with a paired difference. One of the interesting things about a paired difference test is even though you do have 2 different samples of data, they're actually, so we have like a sample mean for like a before group, a sample mean for an after group, for example. Because the data is paired, we're just going to subtract those 2 sample means and do this just like we would do a normal t-test for the mean. So let's do this. So again, let's go to StatCrunch. I already have it open. So t-stats. Yes, there is a paired option. You don't need to do that. Just click on one sample with summary. The sample mean, remember, we're just looking at the mean differences. So the sample mean difference was given to be -8, which you could get just by subtracting these 2 numbers. The standard deviation, we were given the variance. Remember, that's just the standard deviation squared. So just take the square root and you'll get 10, and our sample size is 25. There's 25 paired differences. The alternative hypothesis, we were told, is supposed to be a less than. mu1 minus mu2 is less than 0. So let's select the less than option and click compute. Okay. I didn't really fully read this question. It's asked us for the rejection region to start off with, so let's do that first. To figure out the rejection region, we can do this the same way we did the first question. But we could also just use the table here. We're given that our alpha value is 10%, but this time we're just doing a one-tail test. So we're going to use the, so in other words, 10% is in the tail, just the one tail. So we're going to use that first column. Our degrees of freedom is going to be our sample size, which is 25, minus 1, because it's, again, exactly the same thing as doing a regular t-test. So our test statistic is 1.318, but actually it's the negative of that because we're doing a lower tail test. So it's going to be negative 1.318. And it says round to 2 decimal places, so negative 1.32. All right, now going back to the StatCrunch, we already got our results. Our t-stat was -4. And clearly that falls in the rejection region. -4 is to the left. of negative 1.32. In other words, we are going to reject because our t is less than negative 1.32. So since the observed test statistic falls in the rejection region, HO is rejected, so there is sufficient evidence that that mu1 is less than mu2. As far as our assumptions go, we need, since we have a small sample size, we need the, when we take the differences between x1 and each of the x values, the before and the after x values, we need those distributions to be normal. Remember, we have to assume that whenever the sample size is small. We need it to be random, and that's really all the assumptions we need. Okay, next we want to do a confidence interval. So, oh, I should show what I just did there. We've already set up this, we've already done this test, but remember I did a hypothesis test instead of a confidence interval. If I want to change what option I selected, if I just click on options and click on edit, I can choose the confidence interval option instead, and it says to do a 90% confidence interval, so I'll change that. Again, make sure that your question is the same, or changed accordingly. And so this is my, these are my limits. This is rounded through decimal places, so I'll just copy this carefully. Negative 11.422 and negative 4.578. Great. So basically, the first part has us do a hypothesis test. This part has us do a confidence interval, and it's saying we're basically saying that the differences between the first group and the second group, we can view this as maybe before and after, is somewhere between negative 11.4 and negative 4.6. Both of those numbers are negative, so this is really telling us the same thing the hypothesis test told us, but only with a little more detail. It's saying that the first group's mean is less than the second group's mean. So which of the two procedures, the confidence interval or the hypothesis test, provides more information? Well, I would have to say the hypothesis test, because not only did we get the same kind of conclusion as we got with the hypothesis test, I would say the confidence interval gives us more information, because not only do we get the same information as the hypothesis test, but we also know how big that difference is. We know that difference is at least 4.6, where the first mean is at least 4.6 lower than the second mean. So, there we go. So this would be, for me, option C. The confidence interval provides more information because it gives an interval of possible values for those differences. All right, perfect. Next question that I have planned for us to do is number 9. Okay, this is going to be similar to the last question, only this time we weren't given the summary statistics, we were given the raw data, so let's just bring that data into StatCrunch. Okay, so the question is going to ask us to do a few things. First, it's asking us to find these summary statistics. You could easily do this with a calculator, or create a third column and just subtract these differences, and then do summary statistics for these. Though we can do this automatically in StatCrunch, so let's do that. I'm going to go to Stat, T-Stats, but I'm going to select Paired, because the idea is we have paired samples. We have 6 pairs. All right, so we want to it says here that we should subtract observation 2 from observation 1. So in other words, mu1 minus mu2 is what we're looking at here. So my first sample is going to be population 1, and my second one is going to be population 2. I want to save the differences, and this is going to be important because we might need some of this information. We need to find the sample mean and the sample variance. So let's save those differences so we can run summary statistics on them. And I'm not quite sure if later parts are going to, oh, it says right here, we want to do a confidence interval and we want to do a hypothesis test. So I guess I'll start off with a confidence interval. And I know that's going to want a 90% confidence interval. All right, click compute. This doesn't directly help us with all of part A, but we do have some of the information from part A. We can see that the mean difference is 1. So let me write that down. Great. However, it doesn't give us the variance. It gives us the standard error, which is similar, but like remember the standard error is the standard deviation divided by the square root of the sample size. We don't want that. So, all right, so let's just close this out for now. Let me go to stat, and I need summary stats on this new column that I calculated. So when I clicked this whole save differences, it created this new column, and this column is just the first population minus the second. So 9 minus 8 is 1, 5 minus 3 is 2, etc. So I can click on stat, summary stats, columns, and I just want to find out what the variance is. In fact, I could just select that. I just want to know what the variance is for my differences. Click compute, and my variance is 2. Okay. Next, it says express the mean difference in terms of mu1 and mu2. Well, that's just subtracting them. Next, we want to find a confidence interval, which remember I already did. Any results you get, even if you close it out, they're going to be here under this whole StatCrunch. You can see a number up here that just means how many results you have saved. So let me pull up those results. Okay, so this is what we created before. Remember we found the mean difference was 1, the degrees of freedom is just the sample size minus 1, so that's 5, and we have our confidence interval here, which is negative 0.16 to positive 2.16. So let's write that down. Negative 0.16 to positive 2.16. It says to go to 2 decimal places, and that's why I'm rounding like this. Okay, check answer. Great. Next, we want to find the t-stat, so we need to do hypothesis testing. So again, we can just go to options and edit, and instead of doing confidence interval, I'll select hypothesis test. And I want to test to see if the mu difference is equal to 0 or not equal to 0. That's what the directions tell us to test, to see if the difference is not equal to 0. Okay, so the default's fine there. And our test statistic is 1.73. The p-value, it says to round to 3 decimal places, is 0.144. And so our conclusion, let's see, our alpha value is 10%, our p-value is 14%, so our p-value is bigger than our alpha value, which means do not reject HO, which means there's insufficient evidence that there's a difference. Just to show really quick before we move on to the next question, I could have done this after I got my differences, which again, you can easily just calculate by subtracting each of these numbers to get these differences. Oh, I accidentally have 2 columns here. Let's see if I can delete one of them. Okay. So since I have these differences here, if I went into stat, t-stats, one sample with data, and just did this as if it was a normal t-test, but using the differences column, I would get exactly the same results. See the same p-value, the same test statistic, because when you're doing a hypothesis test or confidence interval for paired differences, it's really just a normal t-test for the mean. The only difference is that instead of these like subscript D's indicating their differences, it doesn't know that you're dealing with differences, so it leaves that out. But it's exactly the same. All right, let's move on to the next question. Let's do number 10. All right, so for number 10, it same kind of idea, only there's a little bit of a story involved. It says that we looked at 78 campers and looked at their weight before and after this camp to lose weight, or their BMI technically, not their weight. All right, so the starting BMI on average was 34.9. The ending BMI, which stands for body mass index, was 32.1. So on average, the campers lost 2.8 pounds each. And the standard deviation was 1.6. And again, this 2.8 is just done by subtracting. So this is a paired t-test again, only they're giving us the summary information. We want to test to see, give the null and alternative hypothesis to test whether the BMI at the end of camp is less than the BMI at the beginning of camp. Keep in mind that the way mu1 and mu2 are being calculated is we're doing starting minus ending. So if the campers did lose weight, their starting BMI would be higher than their ending BMI. So if we want to test to see if their weight went down, well, our null hypothesis would be that nothing happened, so the difference would be 0. Our alternative hypothesis is that their weight at the beginning would be more than their weight at the end, which would cause mu1 minus mu2 to be positive. That's a little bit tricky. How should the data be analyzed? We should do a paired t-test because each person is being sampled twice. Each of the 78 campers we're looking at it wouldn't make sense to view this as two completely separate samples. Obviously, like if your starting BMI is 30, your ending BMI might go up or down a little bit, but it's not going to go to 40 or 60 or, it's not like random where they're completely separate. We're looking at a difference from somebody starting and ending, and because each person's repeated, we really need to use these paired differences because the samples are not independent. Okay, so I'll be honest, I actually answered this question incorrectly my first time because I didn't read very carefully, so we should read this very carefully. It says here, calculate the test statistic using the formula for independent samples. All right, I already know that that's wrong. We've already figured that out in the previous part B, that we shouldn't be using independent samples because it's the same person being measured twice. It wouldn't make any sense for these to be independent. But it says do it with the independent test anyway. So I'm going to do t-test to sample. I just have the summary information. I don't have the raw data set. I'm going to be using, sorry, let me move this over a little bit. All right, so I'm going to be using the starting BMI and ending BMI, not for the pairs, but just as if we didn't pair them. So the first sample mean is 34.9. The standard deviation was 7.3, and our sample size was 78. The second sample mean was 32.1. Our standard deviation was 6.7, and our sample size again was 78. Let's pull the variances. Again, we want to test the greater than. Click compute, and we see our test statistic is 2.4957. All right, let's go back to the question. And we get 495 would then 5 would round the 9 up, so this would round, and then that would round the next number up, so 2.5 up when rounding. Okay, next part, let's calculate the test statistic the correct way using the paired differences. All right, so let's close this out. Let's go to tests, t-test. I want to select the paired difference option, but you see how there's no, like if I click on one sample, it says like with summary, two sample, it says with summary. There's no option for the paired. It forces you to use data. So let me go to the one sample with summary because that's all I have is summary information. And then I have to use the differences summary information that was given to us. So the paired differences, the mean pair differences is 2.8, the standard deviation is 1.6, and again our sample size was 78. We want to test the greater than option, compute, and I get a test statistic of 15.46 if I round. So let's write that. Perfect. So let's compare these. 2.5 might be significant, probably is actually, depending on what alpha you choose, but 15.46 is extreme. Like, this is a very, very large test statistic. Remember, T and Z are very similar. In fact, for large samples, they're almost identical, the distributions. And remember how we talked about the empirical rule, like towards the beginning of the course, how we expect like 99.7% of the data to fall within 3 standard deviations, meaning the z-score should be between -3 and +3 most of the time. So this is extreme, having a T of 15.46. So which test statistic provides more evidence in support of the alternative? Well, yeah, definitely the larger one here, the 15.46. That may not seem that interesting to you, but the point is that you might wonder, like, why would we use paired differences when we could really maybe just use the other one, even though our assumption of independent samples is violated? It's because if you can use paired differences, you really should. You're gonna be more likely to get significant results and find it's a more sensitive test. It's gonna find differences when they're there. All right, the p-value for the test in part 2 was reported to be almost 0, and we can actually see that ourselves. The p-value was 0.0001, or actually it's less than that. It's very tiny. Interpret this at a 1% significance at level. Well, clearly alpha is bigger than p, so you're going to reject HO because the p-value is less than the significance level. Significance level just meaning the alpha value. That means there is sufficient evidence that the mean BMI at the end of camp is less than the BMI at the start of camp. Remember, really, we almost tested the other way to see the mean BMI at the beginning of camp was more than the one at the end of camp, but that's the same thing as saying the mean at the end is less than the mean at the beginning. Same difference. All right. Let's move on to the next question. Number 12 was the next one I had planned. Oops, I forgot to do the last part here. Do the differences need to be normally distributed? No, we actually don't need the normal assumption because remember we have a large sample size, so the central limit theorem applies. And then for the confidence interval, let's just go back to that real quick. Remember, we can switch to a confidence interval just by going to our results, going to edit, selecting the confidence interval option, and changing it to 0.99. Okay, and so this is our confidence interval. It says to round to 3 decimal places, so 2.322 to 3.278. And then interpreting that, we get the mean difference between the BMI at the start of camp and at the end of camp falls, well, remember with confidence interval saying that the mean should be inside the interval. That's always the case. And it's with 99% confidence because we did a 99% confidence interval. Since 0 is not inside that interval, both of these numbers are positive. That's the same thing as our hypothesis test conclusion, that there's sufficient evidence that the mean at the end of camp is going to, well, remember we're doing the mean before minus the mean after, and we're saying that's positive. So if that means that the before is bigger than the after, which means the after must be less than the before. A little confusing, but I think we got it. All right, now let's move on to the next question here. I think question number 12 was the last one we planned on doing, second to last one we planned on doing. Yeah, just the 3 parts are very similar, so I'll just do part A here. Construct a 99% confidence interval for the difference in proportions. This is going to be very similar to doing differences in means. Just select a different option from the StatCrunch menu. So let me go back to StatCrunch. Let's see, we want to do a test for differences, so I'm going to go to proportion stats, to sample. All I have is summary information. I don't have the raw data set. So for the first sample, we have 400 observations. It says N1 is 400. For the second one, we also have 400. The way the software works, it wants the number of successes, not the sample proportion. So we're going to have to do a quick calculation here. So let me just take out a calculator and do that. All right, so if 67% of the sample are successes in the first group, so if I just do 67% of 400, of just means multiply, I get 268. So 268 is going to be my first number of successes. Okay, doing this again for the second part, I'm going to do 0.55 times, again, 400. They don't need to be the same sample size. They just are in this first example. I get 220. It says we want to do a 99% confidence interval. So I'm going to select the confidence interval option. Let's change it to 0.99. Click compute. And those are our answers. It's 0.03 to 0.21. It says round to the nearest thousandth, which is 3 decimal places, so let me do that. Let's see, 0.032 if you round to 0.208. All right, and we don't need to do the rest of this. I mean, you should do the rest of it for full credit, but the rest of it's going to be done the same way. All right, yes, that's fine. Okay, number 13. Kind of similar, but this time we're just doing hypothesis testing, and there's a story involved, making it a little bit more interesting. All right, quickly reading the story here. It says a newspaper reported the planning habits of men and women. As far as what's your preferred method for keeping track of meetings and such, 54% of men and 44% of women said, I keep them in your head. I like to keep the appointments in my head. So just assuming that the sample size was 1,000 and there's 500 men and 500 women, this was an assumption, but that's okay, we can go with that. Let's test this hypothesis to see if, let's see, what are we actually testing here? Set up the null and alternative hypothesis for testing whether the percentage of men who prefer keeping track of appointments in their head is larger than those that, larger than the percentage of women. So basically we want to test to see if P1 is greater than P2. If we subtract P2 from both sides, it's the same thing as saying P1 less than P2 is greater than 0. So A is going to be our first answer here. And again, yours might be in a different order. Compute the test statistic. So let's go to stat, proportion stats, to sample. I just have summary information. I have to assume that there are 500 men and 500 women. Let's do the men first. So it says 54% of men. So 54% of 500, just multiply, is 270. And then it said 44% of women. So 44% times 500 is 220. Okay. And wants us to, let's see, we're doing, we want to find the test statistics, so we need to do a hypothesis test. We want to test the greater than option there. And I get a test statistic of 3.163, if you round to 2 decimal places, is 3.16. It wants us to find the rejection region, so we can use technology for this, or we can just use the final exam formula sheet. The very first page gives our Z table. Really, we don't even need to do it this way. This is a little silly. We could do it this way and find, where the area to the right would be 10%, but that's harder than we need to make it. Another way we could do this is to look at the critical values with the critical rejection regions based on certain alpha values. Table 6.2 is listed as on the formula sheet. It says our alpha value is 10%. We know we're doing an upper tail test. So when our alpha value is 10% and we're doing an upper tail test, we should be testing if z is greater than 1.28. And we're using the z distribution now because we're dealing with proportions. There is no t distribution for proportions. Okay. And then we want to find the p-value for this test. So let's do that. I'm trying. Oops, clicking the wrong window. The p-value was 0.0008. It says to round to 4 decimal places, so exactly how it's given. Clearly the alpha value is bigger than the p-value, or we could say the p-value is less than the alpha, which means there's sufficient evidence to reject the null hypothesis in favor of the alternative. Okay, and I think that's it. As always, just let me know if you have any questions. Mind you, like StatCrunch is fairly intuitive to use, so just click around if you're not quite sure what to click. And you will have multiple times the homework, so don't let it stress you out too much. I know the formulas in this week are very confusing, so if you have any questions, just let me know and don't hesitate to use technology.